Hello class, let's discuss the concept internal forces. Now, we see many structures in our daily lives. All these structures, these are designed or these are placed to carry loads. For example, you see the picture on the left. It's a pillar, it's a column. It has a steel reinforcement and concrete is poured. So what's the purpose? To carry or to bear load. Now, things can fail. For example, you take a bridge, see, given certain amount of loading, they can fail. Why do they fail? Because too much load. And where do they fail? They fail at the weakest section, or they fail at the section where they have too much force due to the external loading. For example, in this picture, right, if you have if you have a loading like that, there are many trucks like this and so on, right? So where does the bridge, if you keep increasing this distributed load, where does this fail? Maybe at the center or maybe at this point. So that is exactly what we need to calculate, which is due to the current loading W, which point here in the beam has highest force acting. At which location exactly do you have huge amount of force that is developed due to the external loading W, which is basically that is called internal forces. So at which location do you have huge amount of internal force developed due to the external loading W? That is the purpose of this chapter. For example, you take a signboard or a billboard. This is the weight W. As you keep increasing the weight, where does it fail? Does it fail on this horizontal member or does it fail somewhere here? Maybe it fails somewhere here, right? How do you know that? Because we have to calculate internal forces at every location. So internal force here, internal force there, there. At every location, we calculate something called internal force. And that location where you have huge amount of internal force, more chances are there for that to fail. So that is why we need to study something called internal forces. Same sort of application here. Let's say you have weight W. As you keep increasing this weight W, what happens to this joint? Imagine this kind of external reinforcement is not present. That means this joint has more chance to fail. So to increase the strength of this joint, we have this external reinforcement like this, right? How do we know that this is the weakest? Because of calculations. So I'm going to show you how to calculate internal forces. How to calculate these internal forces. For example, let's say there is a structural member. In this case, I'm showing you AD. And there are some loading. Now 6 kilonewton force acting at 3 meters from the left edge. 9 kilonewton times meter is a moment acting at D. So due to this external loading, what is this? What is the external loading? Like I said, external loading is 6 kilonewton vertical force acting down, 9 kilonewton times meter acting at point D in counterclockwise direction. These two are external loadings. Due to these external loadings, my question is, what is happening to point B? Or what is happening to this point? If I ask you specifically, tell me what is happening to this section here. What we are supposed to do is we have to do method of sections. That means we have to create a section. That means we have to have an imaginary cut. For example, in this case, there is a loading AB. So let me draw AB on the right hand side. So there is AB, and at A you have a pin joint. At D, no, at A you don't have a pin joint. You actually have a slider or a roller. At D you have a pin joint, and you have 6 kilonewton force acting at B, and you have an external load 9 kilonewton times meter. So if the question is what is happening to a point at B? Now at B there is a discrepancy. That means at B, exactly at B, you have 6 kilonewton force, but slightly to the left of B, slightly there. Just it is exactly at B, but slightly to the left of B, what is happening? And slightly to the right of B, what is happening? If I'm asking you what is happening in the sense, my question is, what are the internal forces at B? Means slightly to the left and slightly to the right, because exactly at B you have 6 kilonewton force. When I ask you that kind of question, we have to do something called method of sections. That means we imagine an imaginary cut. That means we cut this beam AD, we cut it. We cut it into two at B, and then we take one piece, either the left piece or the right piece. It's up to us. I'll take the left piece because on the left piece I just have the slider, I just have the slider, and there's nothing else, right? On the left piece there is no force acting. There is no 6 kilonewton force. The 6 kilonewton force is acting on the right piece. So if I take the left piece, that means if I take this part, right? If I take this part, there's no 6 kilonewton force except the slider, right? So what I'll do is I'll take the left piece. So when I take the left piece, I consider the left piece. So I redraw this again. So exactly at B, I'm making a cut at B. And at A, I have the slider. And at B, I made a cut, and this is 3 meters. The rule whenever you make a cut is you have to represent 3 reactions. One is normal reaction at B, second is shear at B, third is the moment at B. Whenever you make a cut, and the reason we have to make a cut is basically to find these 3. Those 3: shear, normal, moment. You already know what is a moment. You know what is a normal force. Normal force, if you take a beam, for example, or you take a column, if there's a force acting, and if the force is acting perpendicular to the surface, we call it normal force. If a force is acting parallel or along the surface, we call it shear. For example, let's say we take our shoes. For us to walk, what we technically do is we push the ground, so we move forward. So that force which is acting along or parallel to our surface of the feet is the frictional force, FF, frictional force. We can consider that it is a form of shear force, that means which is acting along the surface. But you see, if you're just standing still, our weight is acting down, but what is balancing us? What is balancing is the normal force from the ground, right? For us to walk, it is frictional force, which we can treat it as shear. And for us to just stand still, there is a normal force, which is perpendicular to the surface of our shoe. That is normal. So normal force is perpendicular to the surface. Shear force is parallel or acting along the surface. And you already know what is moment. Moment is a rotational effect that is caused with respect to uh, certain point. So these three are called internal forces that are generated at at the point B. So if I'm asking you, hey, what is happening to this point, and let me call this point, I need to see there, right? Yeah, let me call this C. If I'm asking, oh, wait a second, I'm just waiting for this to sync. OneNote has problem syncing. Sometimes it takes a little while, but we'll continue the discussion. For example, I ask you, hey, what is happening to a different point? Let me give a point between B and D, right? I'm showing, yeah, this is the point C. It's syncing now. That's the point C. If I'm asking you what is happening to C, what will you do? You make a cut, imaginary cut. And when you make a cut, you have to draw three things: normal, shear, moment at C. That means you have to draw something like this, right? And this is at C, so you have to draw normal at C, you have to draw shear force at C, you have to draw a moment at C, and you're taking the left piece. See, whenever you make a cut, you have to either take the left piece or the right piece. For example, if you take the left piece, this is what you're supposed to do. And on the left piece, don't you also have 6 kilonewton force acting 3 meters from the left? Yes, you do. And this is some other distance x maybe. I'm going to give you the distance x for this point C. Right? You may ask me, oh, then why did we not draw 6 kilonewton force when we took the section AB? Is that we made a cut slightly to the left of B. We didn't make a cut slightly to the right of B. If we made a cut slightly to the right of B, yes, we have to also consider 6 kilonewton force. But in this case, I took a cut slightly to the left of B. That means at 6 kilonewton force, that means at the location where you have an external force or external support present, there is a discrepancy. So you have to make a cut to the left, do the analysis for VB, NB, MB, and you have to make a cut slightly to the right. That means you have to make a cut slightly to the right like this. When you make a cut slightly to the right, you have 6 kilonewtons, normal at B, VB, moment at B, and you take the slider support. So you make a cut slightly to the left of B, slightly to the right of B, and the distance will be almost the same, 3 meters. I mean, To be more accurate, what I'm supposed to write is I have to write it as 2.9999 meters. And here, what I'm supposed to write is 3.00001 meter. Right? So 2.999, I'm approximating this to be 3 meters. And 3.001, I'm approximating it to be 3 meters. And I'm calculating what is happening slightly to the right, because in this case, the difference is that there is the presence of 6 kilonewton force. That means the values of VB, NB, MB are different. Here, the values of VB, NB, MB will be different because there is no 6 kilonewton force present. That means just before B, internal forces are different compared to what is happening slightly after B. So if I'm asking you what is happening to a point inside a beam, what are you supposed to do? You have to make an imaginary cut and draw three things: shear, normal, moment at that point, and find those values, because that is technically a free body diagram, though it's not complete, because at A, whenever you have a slider, you have AY, right? If you have a slider at A, you have AY, isn't it? I already drew that. It's going to take a little while to sync. So at A, because A is a slider support, you have AY. So you have to use the value of AY to calculate VB, NB, and MB. And that's what I'm going to show you in a little while. Yeah, now it's synced. So we have AY reaction. So the process is as shown here. So in this example problem, what I've done is I'm asking you what is happening to what is the internal force at B or slightly to the left of B. When I ask you that, you have to make an imaginary cut and draw these three things. So here you see AY, VB, NB, MB. So you have to draw these three things and AY. So in a 2D problem, how many unknowns can you solve? You can solve for 3. Because if you remember, you have 3 equations: sigma fx equal to 0, sigma fy equal to 0, and moments with respect to a point, some point, is equal to 0. So you have 3 things, or you have 3 equations. So you're using these 3 equations, you can solve for 3 unknowns. So the 3 unknowns are VB, NB, and NB. But see, in this free body diagram, yeah, you don't know VB, you don't know NB, you don't know MB, but do you know AY? According to my diagram there, no, I don't know AY. So before you make a cut, that means before you make an imaginary cut and draw VB, NB, and MB, you have to find what is the support reaction. And do you know how to find a support reaction? Yes, you do. In the previous chapters, I taught you how to find support reactions. So the way this chapter works is, just a sec. The way this chapter works is, number 1, decide which piece you want to consider. For example, in this case, if I'm asking you find internal reactions at B, do you want to take AB or BD? Look at the picture on the left. Do you want to take AB? That means you want to take this piece, or do you want to take BD piece? You have to decide that first. Which piece you want to consider? Let's say you want to consider AB. Then find all the support reactions present in that piece. For example, you want to consider AB, find AY. That means before you make a cut for this given picture, for this given loading, can you find AY? Yes, you can, because you can apply sigma fx equal to 0, sigma phi equal to 0, sigma m equal to 0. You can apply many things to find AY. Let's do that. So just let me complete the procedure. Find all the support reactions present in that piece. Finally, then make a cut and consider that piece and solve for the internal reactions. Right? Then make a cut and consider that piece and solve for the internal reactions. At the section where you made the cut. Okay, where you made the cut. So let's follow the same procedure here. Number one, which piece do I want to consider? Okay. Okay, so these are the steps, right? So which piece did we decide? I said I'm going to take the left piece, AB. So in the AB piece, so first of all, step number one is done. I decided which piece I want to consider, AB. So find all the support reactions in the piece. What supports are there? What supports are there in AB? There is a slider support at A. That means in the free body diagram, there is AY. See, there is 6 kilonewton force. And there is this point D, which is a pin. That means you have dy, we have dx, and there is external moment of 9 kilonewton times meter acting at D. So this is the free body diagram of the original, or this is the free body diagram of the given system, right? First of all, we have to draw the free body diagram of the given system. Then, so this is the free body diagram. This is x, that is y. I gave all the distances, and there is no force which is at an angle, so the free body diagram is complete. Now for this free body diagram, what did I ask you to do? Find all the support reactions present in that piece. So if I'm considering AB, that means if I want to consider AB in the future, because I'm asking you to find what are the internal reactions at B, that means we have to take the cut at B and consider AB part, which is what we will do later. But before we do that, what we need to do is we have to calculate all the support reactions. So what are the support reactions in that piece? That means in AB, because I wanted to consider AB. What are support reactions in that piece? Support reactions present in AB are just AY. So I just have to find what is AY. So what will you do? How will you find just AY? You may say, I'm going to use an equation sigma Fy equal to 0. That implies Ay plus dy minus 6 is equal to 0. Can you solve for this now? No, you can't, because you don't know what is dy. Rather than doing this, what I will do is I'll take moments with respect to d equal to 0. If I take moments with respect to point D, right, dx and dy are already cancelled because the distance is 0. So a smart way to do is this approach here. So take moments with respect to d equal to 0 with respect to d. I already have 9 kilonewton meter in counterclock. So I'm going to write plus 9. It's counterclock. Then we have 6 times 6. This is 6, 6, and that is also counterclock. Plus 6 times 6. So that's a counterclock, right? Then we have ay. We have ay times 9, and with respect to d it is clock, so I'm going to write negative is equal to 0. So find what is ay. Ay would be 9 plus 6 times 6 is 36 over 9. I'm just rearranging it quickly. So ay would be 1 plus 4, which is going to be 5 kilonewtons. So ay is 5 kilonewtons. I already found that, right? Now we have to go to the third step. What is the third step? Then make a cut. Now you're going to make a cut and consider that piece. So now you make a cut and consider that piece. And which piece did we decide when we started the problem? We wanted this. We wanted to take A, B, right? So now let's make a cut just to the left of B, right? Just to the left of B. So for this part, what I'll do is I'll make a cut just to the left of B, right? And A, what is AY? AY, we just found out AY to be 5 kilonewtons. And whenever we make a cut, what did I just tell you? You have to draw three things: normal at B, shear at B, moment at B. And this is at 3 meters. And because you're making a cut just to the left of B, you don't have that 6 kilonewtons. But if you make a cut to the right of B, you will also have to draw the 6 kilonewton force. Now the free body diagram is complete. This is X, that is Y. Now you have to solve for VB, NB, and MB. How do you do that? You have three equations. Sigma of x equal to 0, assuming to the right is positive, implies you have NB equal to 0. Easy, isn't it? 0 kilonewtons. Then sigma of y equal to 0 implies positive 5 negative VB is equal to 0. That implies what is VB is going to be 5 kilonewtons. Last thing, moments with respect to B. It is B. That's where you have B is equal to 0. Assuming counterclock is positive implies you have 5 times 3, and that is clock negative, and you have positive MB equal to 0 implies what is MB? 15 kilonewton times meter. So these are the internal forces at B. So if I ask you what are the internal forces at B, you make a cut slightly to the left. I'm going to be more detailed in the question that I ask you. So I'll ask you, what are the internal forces just to the left of B? Then you have to make a cut like this. Solve for NB, VB, MB. So if I ask you, hey, what are the internal forces to the right of B? What are the internal forces to the right of B? What will you do? So if I ask you what are the internal forces to the right of B, what will you do? You have the same thing, but at B, you have the 6 kilonewton force. This is to the right of B, just to the right of B. Then you apply the same drill. What is the same drill? Sigma fx equal to 0 implies you just have nb equal to 0. That remains the same. Sigma fy equal to 0 implies we have positive 5, negative 6, negative vb equal to 0. So how much is vb? You have negative 1 kilonewton. Sigma moment with respect to b equal to 0 implies you have 5 times 3 clock negative positive mb equal to 0. So mb is 15 kilonewton times meter. So if you look at these both, nb remained the same, both are the same. mb was also the same, but the difference was in vb, the shear force. There is a difference in the shear force if you made a cut just to the left and just to the right. So there will be a difference slightly. So this is an overall process on how to calculate internal forces at certain point. So let us proceed further and do some more problems. So this is theory. How to calculate the internal forces at certain section is, you make a cut and you represent three things: normal, shear, moment. For example, you want to consider the right piece, you make a cut normal, shear, moment. And these are the steps. You have to make an imaginary cut at the place where you need to determine the internal forces. And you have to decide which section or piece will be easier to analyze. Then, depending on which piece, right? So here, depending on which piece you want to consider, you have to calculate any support reactions or joint forces in that piece or in that section. Then you have to consider that piece, draw the free body diagram of the piece, represent normal, shear, moment. Like this, represent normal, shear, moment. Apply equations of equilibrium, solve for the unknowns. So that's the overall process. So now that I presented this, take some time to digest, go over this approach, right? Go over this approach. Then let's solve this problem. So let's solve the problem. So that problem, I'm asking you to calculate internal forces at C. So engineers tell me, I'm asking you to calculate what are the internal forces at C. So engineers, you tell me which part or which piece do you want to consider? You want to consider the leftmost, all this piece, or do you want to consider this piece? I would want to consider CB. I want to consider this rightmost piece because all that is present is just a pin joint. And if I can calculate what is BX and BY, problem is done, isn't it? I would want to consider CB. It's up to you. If you want to consider this left piece, it's up to you. It's fine. So according to the steps, what did I ask you to do? If you consider the right piece, you have to calculate the support reactions present in that piece. That means I'm asking you to calculate what is Bx and By, right? So to do that, what we have to do is I have to draw the free body diagram of the given. I have to draw free body diagram of the given um, given loading, given problem. So let me draw the beam, and at B it's a pin joint, so I'm going to draw Bx and I'll draw By, and at A you have a roller support, so I'll remove the roller, but I'll represent that with roller support gives just the normal reaction, so it is just AY, vertical reaction up, and there is this distributed loading. Um, is our free body diagram complete? This is X, that is Y. No, the free body is not complete because I did not give you the distances. That is 9 feet. This is 6 feet. That means given is a distributed loading, and I'll represent the distributed loading with one single force, and that would be how much? Kilopound per feet. So 3 times 3 kilopounds per feet is the distributed load. So what will be the equivalent load? That will be 3 times 6, that will be 18 kip. Kip means kilopound, right? Now the free body is complete. Now our aim is to just find what is Bx and what is By. That's it. The reason, because we are interested in the point C, which we will eventually make a cut, and we will consider CB. So because that is our aim, I want to calculate what is Bx and By. To calculate Bx, sigma of x equal to 0 is an useful equation. Seems like we just have Bx equal to 0, so Bx is 0. To calculate By, we'll use sigma Fy. No, I'm not going to use sigma Fy. I'll use sigma moment with respect to A is 0. Assuming counterclock is positive. The reason, if I take moments with respect to this point A, Ay will anyways go to 0. Ay times the distance is 0, so the contribution of Ay towards moment is 0. I'll be just left with By. I can directly calculate By. So one equation is enough for me to calculate By. So if you write sigma Fy equal to 0, if you write sigma Fy equal to 0, you would be getting Ay plus By minus 18 is equal to 0, and you don't know what is Ay, and you can't calculate By. So you have to calculate Ay first to calculate By. So I'm not going to use this equation, though the equation is correct. What I'll do is I'll write sigma moment with respect to A equal to 0. That implies we have 18 times, because 18 acts exactly at the center, 3 feet. 18 times 3, and with respect to A, it is counterclock, positive, and with respect to A, By is also counterclock, so positive By times 9 is 0. That implies By is negative 18 times 3 over 9. So By seems to be 2, 9, this is 2, 2 times 3 is 6, negative 6 kilopound. What is the meaning if By is negative? That means our assumed direction is opposite. We have to flip the direction, but I'm not going to flip it. I'm just going to use this By equal to negative 6, highlight it, leave it like that. Now what we will do is we will make a cut and we will consider the CB section. So because we will consider CB, what I'll draw is I'm making cut at C. I'm taking CB. BX is anyway 0, so I'll not even draw BX. So BY, what is BY? We just calculated BY to be -6 skip. It's fine, write negative in the free body diagram. It's okay. See, in the original system, you assume BY is going up. Stick to that, stick to that original assumption. Okay, it's fine. 6, and then now you make a cut at C. What should you do? You should draw normal at C. You draw shear force at C. You draw moment at C. And you draw X, you draw Y, and VC is, what is this distance? 4.5 feet. That's it. Now you apply the three equations. Sigma fx equal to 0 and C is equal to 0. You already got that. Sigma fy equal to 0. You get positive VC, positive uh, -6 skip, 0. That means VC is basically 6 skip. Right, positive, and this is by, right, and by came out to be negative. That's why I just wrote positive -6 feet. -6 skip is 0. Sigma moment with respect to C is equal to 0 implies moment C, and moment, how is the moment C? I assume moment C is going clockwise. It's my assumption, it's up to you. I assumed it's going clock, so I wrote it negative. Then what else is present? Then this -6 times 4.5, and this is, how is this? It is counterclock, isn't it? It is counterclock with respect to C. So I'm going to write positive. The force, which is -6 times the distance, 4.5, 0. That implies, what is MC? -6 times 4.5. So this positive is because it is going counterclockwise. And this -6 is because we just calculated by is -6. So don't get confused. It is going counterclock, so it is positive. So 6 times 4.5 kilo-pound times feet, kip times feet. So moment would be 6 times 4.5, how much is it? I got 27. So it's -27 kip feet. Highlight that. Problem is over. Wait a second. So here, by, so the positive is counterclock. This -6 is because we calculated by to be -6. This is the moment. That's it. That's the problem. That's how we do these problems. So we see in the solution, he got -6. How much did we get? We got +6 because in the textbook that I follow, the author took going down. So he assumed VC is going down. I assumed VC going up, and I got positive. He assumed he is going down. He got negative. It's fine. And he assumed clockwise, exactly how we assumed. We assumed it's going clockwise, and we got -27. He got -27 kip times feet. So that's how we do these problems. So how to do this problem? Excuse me. How will you do this problem? I'm asking you, what are the internal forces at C? What is your idea? What's your idea? Which part do you want to consider? Do you want to consider AC or CB? You think CB is too complex? Let's just take AC because it's simpler. It looks simple. So if you want to consider AC, you have to first of all find what is AX and AY because A is a pin joint. So in the given system, so let's draw the free body diagram of the given system. So this problem, I'll be a little fast. So for the given system, you have AX, you have AY, and here you have this rope, and that is being given tension 400 Newton. And this is B, it's a roller, it's BY, this is X, that is Y. I have to give all the distances. So this is 3 meter, this is 2 meter, right? This is 1 meter, and the radius is given as 0.2 meter. Okay. Then that is the free body diagram of the given system. Then you have to find, so our aim is to find what is AX and what is AY. That's our aim. So to find AX, let's use sigma Fx equal to 0 implies positive AX, positive 400 because 400 newtons is going to the right is equal to 0. Hola, we found AX is negative 400 newtons. Great. Then next thing is sigma Fy equal to 0 implies. Should we use sigma Fy equal to 0? No, we'll have AY and BY then. No, I would rather use sum of moments with respect to B equal to 0 so that I can neglect BY. Then what we have is we have AX is also passing through the point B. The line of action of AX is through B, so we can also neglect AX. Then we have AY times, what is the distance, perpendicular distance between line of action of AY and the point B is 5 meters. AY times 5, and with respect to B, it is going clock, so it's a negative. And 400 times, isn't it 1.2? So the line of action of 400 is like that. The line of action of 400 is like that. So with respect to B, the distance between 400, the line of action of 400 and the point B is 1.2, and with respect to B, it's going clock. So I'm going to write negative. So negative, oh, wait a second. I have to write negative here, 0. That's it. That means what is AY? I got AY to be negative 400 times 1.2 over 5. So 400 times 1.2 divided by 5, I got 96. So AY, I got it to be negative 96 Newton, right? Now we found AX and AY. So what's the next step we have to do? We have to make a cut and take the left piece. So now what we are going to do is, because the point C is somewhere here, it's exactly 1.5. So that's where the point C is. So what I'll do is I will take a cut AC. I'll take the leftmost. So that is the C. So I'm just waiting for this to sync. Yeah. So this one, I'm making a cut. So at C, you have normal at C, you have shear force at C, you have moment at C. Then at AX, how much is AX? Negative 400. How much is AY? According to our consideration, negative 96. Newton. That is 1.5 meter. Now my question is, how will you solve for VC, NC, MC? That's pretty much three steps. Sigma fx equal to 0 implies NC plus negative 400, because for negative 400 newtons is going to the right. So I wrote this positive is because it's going to the right, and negative 400 because of its value. We found out AX because we assumed AX was going to the right, and I got negative 400 newtons. So I still wrote AX going to the right is negative 400 newtons. So from this, negative 400 equal to 0 implies NC is 400 newtons. Sigma Fy equal to 0 implies we have positive negative 96. Positive is because it's going up. Negative 96 is because of the value we calculated just now, right? I assumed AY is going up and I got negative. I still write the same thing. AY going up, it's negative. Negative 96. Negative VC because I assumed VC is going down, the direction. And any other thing in the y direction, nothing. That's it. Is equal to 0 implies VC is negative 96 Newton. Moments with respect to C equal to 0. So this is the point C. Assuming counterclock is positive implies I have negative 96 is the value times 1.5. Force times 1.5. And that is going, this is going clock. So I have to write negative, and this is because clockwise. Again, what is this negative 96? It's the value we calculated. So don't say, oh, I think I have negative here. Should I again write negative? Don't get that much confused. Negative 96 is basically the value we calculated, and this negative is because clockwise. Then what else we have? 96 times 1.5 is going clock, and then MC, we assumed it's going counterclock, is 0. Then what is MC? That implies MC is negative 96 times 1.5, which is 96 times 1.5, which is 144, negative 144 Newton meter. So the internal reactions at sea due to the given loading, that means when you had a rope with this pulley system, you apply 400 to the right, internal reactions at sea, internal reactions at C are, normal reaction is 400, going away from C. That means, isn't the NC going away from C, perpendicular to the surface? That means C is in tension. VC is negative 96. That means actually VC is going up 96 or down negative 96. Moment is 144 Newton, and I assume counterclock. That means it's actually going clock 144 Newton meter. So basically, that's what we calculated. NC, VC, MC. That is how we solve problems. So I'll help you solve one more problem. This is also important here. And then you should be practicing the same problems I discussed in the slides. So you can solve problems related to what I presented here in the exam. So here, I'm asking you to find what are the internal reactions at C. At C, point C, what will you do? Will you take AC part or will you take C to almost to the rightmost? I would take AC. That means what are you supposed to do? You have to find what are the support reactions at A first, right? What are the support reactions at A? How will you find that? Take free body diagram of the given system. Same drill. Take free body diagram of the given system. You have a pulley, seems you have a rope, and that is tension T, and T is not given. And that radius is 0.5 feet, and this is at 2 feet, and you have a distributed force, and at A you have AY and you have AX. And why did I draw AX negative? It is just comfortable for me to draw because if I draw into the picture, I have to erase many things. It's just my assumption. I can draw to the left or to the right. This is my X, that is my Y, and the distributed load is 150 pound per feet, and this whole thing is 8 plus 4, 12 feet. Then what else? Am I missing something? That's pretty much it. So what is the equivalent force due to this distributed load? It exactly acts at 6 feet from right or left. Then it is 150 times 12 pounds. How much is 150 times 12? 1800. So it is 1800 pounds, and it is acting at 6 feet because it's acting directly at the center. That's it, right? Yep. Now that's the free body diagram, and our aim is to find AX and AY so that I can take the AC part and do the calculation. So how do you find AX and AY? AX and AY, you take sigma fx equal to 0 implies sigma fx equal to 0 implies negative AX because I took AX to the left there in the free body diagram, and negative T negative AX negative T, that's it, equal to 0. Wow, that means I have to find T to find AX. There is no other way. Then sigma Fy equal to 0 implies we have AY and we have negative 1800 Anything else in the y direction? No, that's it. Is equal to 0. And what else we have? Oh, we found AY here. AY is basically 1800 newtons, not newtons, sorry, pounds. One thing is done. Then we have to find AX. That means we have to find T. So there's no other way. We have to find T. So let's take moments with respect to A equal to 0 implies, I'm just waiting for this to sync. Give me a sec. It'll sync eventually. I'm waiting for this to sync so I can show you what I wrote now. Anyways, I'll keep writing so eventually it's gonna sync. Is it a problem? Sync. Yeah, it's synced now. Okay. Moments with respect to A equal to 0 would be T times 2.5, and it's a counterclock positive. So because it's C, with respect to A, T is going like that, counterclock. T times 2.5. Then what else? Moment with respect to A. T is done. AX, AY, they are at A, so they can be neglected. We have 1800. Oh, wait a second. 1800 times 6 with respect to A, and it is going clockwise, so it's negative, is equal to 0, implies we can calculate T to be 1800 times 6 divided with 2.5. I got 4320 pounds. So we can calculate AX from there to be basically negative T. That implies AX is negative 4320 pounds. Negative 4320 pounds, AX. Now we take AC, right? Now I'll take AC. Now, for example, if you think, oh, AX, I found this out to be negative, it is getting more confusing for me to use these negative values. What you can do is, for example, uh, just a sec, it's syncing. Some internet error, it's syncing. Okay. Uh, For example, AX is negative 4320, and we want to consider the left part AC. So let me draw the free body diagram of AC. So I'm not sure why it's t- so, yeah, now it's synced. Okay, it's a small problem with internet. So where is the C? C is 3 feet from left. That's where C is. So what I'll do is I will draw the free body diagram of AC like that, and I made a cut at C, and I'm considering the A part. Now, listen to this carefully. Now, I assumed AX is going to the left, and I got negative. Like we did in the last problem, I can consider this going to the left, and I can write a negative value here, which is negative 4320 for AX pounds. But for example, if it is confusing to have this negative number there, what I will also recommend you to do is you can flip the arrow in this free body diagram and make this positive. So let's see this AX here. I assumed it's going to the left and I got a negative number. So in the new free body diagram, I make it going to the right and make this positive so that there's less confusion. It's up to you. So, and this is 1800 pound, and that is for the AX and AY. And at C, I made a cut, so I have to draw three things. Normal at C, shear force at C, moment at C. And this is 3 feet. Okay, now let's work with this sigma fx equal to 0 implies 4320 plus nc is 0, so nc is negative 4320 pounds. Sigma fy equal to 0 implies positive 1800, negative vc is 0 implies vc is 1800 pounds. Negative vc is, and then so I'm going to write it here, vc is 1800 pounds. So I will erase this part so I can fit that in the screen. Yeah, vc is 1800 pound. Then sigma moments with respect to c equal to 0, assuming counterclock is positive, implies what do you have, mc is anyways, I assumed it's going counterclock, so I'm going to write positive, and I have 1800 times 3, that's clockwise, so it's negative with respect to c is equal to 0 implies what is mc, it is 1800 times 3, it is 5400 pounds. No, pound feet, right? Pound feet. I'm sorry. Seals. That's it. That's the problem. Oh, we got some wrong answers. We got something wrong. NC VC is 1350. Oh, we did something wrong here. Yeah. Thing is, I'm sorry. I got carried away too. So yeah, when you make a cut, this is important. That's the whole point I wanted to present this problem. Engineers, when we make a cut at C, yeah, we drew VC and CMC, that is correct. See, when you take this part, see, when you take this part, isn't there a distributed load? We conveniently ignored that. That's wrong. Even if you take slightly to the left of C or slightly to the right of C, we have this distributed load, isn't it? We have the distributed load between A and C, isn't it? Yeah, we do. And did I draw that in the free body diagram here? No, I didn't draw it. So we have to draw that. So there is no effect on sigma fx because the distributed load is in the y direction. So what I'll do is we have to rework the problem from y. So what I'm going to do is we have to draw the distributed load which is, how much is this? 150 pound per feet, and it is acting all along this 3 feet, isn't it? So this is 150 pound per feet. It is acting on this 3 feet. So what is the equivalent load due to the distributed load? That would be acting at the center, right? That would be acting at the center, and that would be 150 times 3 pounds. What is 150 times 3? 450 pounds, right? That's 450 pounds. And that is acting at 1.5 feet from the left edge, or because it's the center, even from the right edge. Now, if we take sigma Fy equal to 0, we have positive 1800, we have negative 450, negative Vc equal to 0. That implies Vc would be 1800 minus 450. We get 1350 pounds. So that is the correction that I want you to make, and that is an important thing that you need to understand, right? Then the moment. Sum of moments with respect to c equal to 0, we have 1800 times 3, it is going clock, so it's a negative, and we have a positive 450 times 1.5. So this term was missing um, in the previous case, positive 450 times 1.5, because it is going like this with respect to say positive counterclock, because it's going counterclock. And we have MC, and we already assumed MC is counterclock, is equal to 0. So what is MC? MC would be 1800 times 3 is 450 times 1.5. I got 4725. I got 4725 pound feet. Now let's check the answers. Yep, now we are correct. So that is this. So that is this example problem. So this is what you need to understand when I'm asking you to calculate internal forces. Okay. So rework all these example problems again. Okay. All the best. Stay safe.